Welcome to section 9.3 from our textbook, Property of Logarithms. In 9.2, we're introduced to logarithmic functions and how logarithmics and exponentials undo each other. Today, we're looking at certain properties of logs, that log function. And so in the big red box on your screen right now is 3 of the 4 properties we'll be talking about today. Very important that you understand these. So I might pause the video really quick, write them down, and then click play so you can hear my explanations and just focus on hearing it and not writing them down at the same time. So I'm going to go through these and give you examples of each one before we start jumping into problems. So first one, log base b of m times n equals log base b of m plus log base b of n. If we have a log of some product, we can actually split it up into individual log functions of that product's factors added together. Now, I just used a lot of math words, I realize that. But let me give you kind of a concrete example for this. Log base 2 of 6. Well, I know that 6 is 2 times 3, right? We know that. So that means I could rewrite this as log base 2 of 2 plus log base 2 of 3. And it will equal the exact same thing. Log base 2 of 6 equals log base 2 of 2 plus log base 2 of 3. Why would this be useful? Well, maybe I don't know what log base 2 of 6 is, but I'm given information about log base 2 of 2 and log base 2 of 3. Well, now I can solve the problem. I didn't know 6, but I know 2 and 3. I can just add them together because I understand this property. When we have log base b of some product, and in this example it was 6, we can break it up into individual logs of its factors added together, 2 and 3. So if multiplication becomes addition, what does division become? You might have guessed it, division can become subtraction. Log base b of m over n equals log base b of m minus log base b of n. Example time here, log base 7 of, I will say 8. I could rewrite that as log base 7 of, I'm not going to do 64, I'm going to do 16. Minus log base 7 of 2. Because 16 divided by 2, look back at the property there. If in this example, m is 16, and n is 2. So we could do log of 16, log base 7 of 16, minus log base 7 of 2. What else could I do? It doesn't have to just be 16 and 2. Could I do log base 7 of 24 minus log base 7 of 3? Absolutely. 24 and 3, 24 divided by 3 would still give me my 8 that I'm looking for. So again, we're going to do whatever is convenient, whatever information we have, and you'll see this in many practice problems down below. So I think you'll definitely get the idea then if you're not seeing it now. But we are given some information, we know some information, we are rewriting these logs into things we know so that we can find the answer. Last property we're talking about right now, log base b of b is 1. Easy one for me to come up with examples for. Log base 12 of 12 is 1. Log base 71 of 71 equals 1. If the base and then what's inside that logarithmic function match, it equals 1. Which makes a lot of sense when you think about it. Think back to 9.2, the loop. This is saying 71 to the first power equals 71. Yep, anything to the first power is itself. So just some examples to hopefully help understand those properties. Let's see them in action. So 2 problems here. Now, I want you to read what I kind of copied from your textbook there. It says, use log base 5 of 2 equals approximately 0.4307. And log base 5 of 3 is approximately 0.6826 to approximate the value of each expression. So we know two things. We know what log base 5 of 2 is. We know what log base 5 of 3 is. And we actually know a third thing. There's one that we always get for free. And it was our third property. What is log base 5 of 5? It's 1. That's our third property with whatever base we're working with. We know these three things: log base 5 of 2, log base 5 of 3, those were given to us. Log base 5 of 5, we know. I don't know log base 5 of 50, but if I can rewrite 50 in 2s and 3s and 5s, we'll be in business. So I look at this and I say, well, okay, 50. What is 50? Maybe can I break it down into factors that are smaller, 2s, 3s, and 5s, that I can then add individual logs together. So I break down 50 maybe with a tree, almost like a square root. That's 25 times 2, that's 5 times 5. So 2 times 5 times 5. I just like putting them in order. Well, this is good news because I know what log base 5 of 2 is. I know what log base 5 of 5 is. Using my first property, sorry, I miswrote that, log base 5 of 2 plus log base 5 of 5 plus log base 5 of 5. I am taking each factor and making it its own individual log that I then add together. This was my first property in action now. So what was log base 5 of 2? I was told it's approximately 0.4307. What is log base 5 of 5? 1. 2.4307 approximately. Log base 5 of 50, 2.4-ish. Now, how can we check this? What does that even mean, really? If you think about what's written here and what our answer is, and I'll combine them for checking purposes, this is saying log base 5 of 50 is approximately 2.4307. Think of our loop. 5 to the this, does it equal 50? Let's check. 5 to the 2.4307, does it equal 50? 50.00188645, pretty darn close. And the reason it's off by a bit is because we didn't have an exact value for log base 5 of 2, right? They said approximately 0.4307. So it makes sense that our answer would be a tiny bit off if they rounded a bit, and sure enough it is. But if you get 50.00, that's pretty much 50 for our purposes. Because they rounded, we can feel pretty confident in our work. I want you to try the second one on the screen. Log base 5 of 30. Pause the video, try rewriting it in its factors, maybe break them up, add them together. I'm gonna pause my video and then I'll unpause with the work and the answer on the screen. All right, and there is my work, breaking 30 down into 2 times 3 times 5, splitting it up into those individual logs, adding them together, because I know each of those values. I'm getting 2.1133, and I did check it on my calculator, and it equals 30.0008. Once again, that's about 30. They rounded in the values they gave us, those highlighted ones at the top, so it makes sense that our answer is a little bit off. Cool, let's do another one. Log base 4 of 2. So we know what log base 4 of 2 is. Excellent. And we also know 1 for free. I also know what log base 4 of 4 is. So I'm just going to write that down to remember it. And we're asked, what is log base 4 of 32? 4 to the what equals 32? So I'm looking at 32 and I'm saying, okay, so 32 is 4 times 8 is 4 times 2. And maybe I stop there because I know what log base 4 of 4 is. I know what log base 4 of 2 is. So I could say log base 4 of 32, that's what I'm being asked, is log base 4 of 4 plus log base 4 of 4 plus log base 4 of 2. Since 4 times 4 times 2 equals 32. That's 1. That's 1. That's 0.5. 2.5. And I can check it. 4 to the 2.5th power, sure enough, equals 32. So part of this lesson is going to be showing you various things with these properties. What if you didn't stop 32 at 4, 4, and 2? What if you said 32 is 4 times 8, which is 2 times 2, 2 times 4, 2 times 2? Would we be in trouble? Would this still work? Because this would seem to indicate that log base 4 of 32 could be written as log base 4 of 2 plus log base 4 of 2 plus log base 4 of 2. And it looks like there are 5 of them. 2. And there's the 5th one. And if we gave, the value they gave us was that this was 0.5, 0.5, 0.5, that's 1.5, that's 2. Sure enough, it does equal the same thing. So no matter how you break it down, where you stop, as long as you do it correctly, we will end up with the same correct answer. A little bit of peace of mind there. That blue one was kind of painful though, writing log base 4 of 2 out 5 times and adding all of them together. Is there an easier way? Yes, there is. And that'll be, I mentioned at the beginning, I said 3 of the 4 properties. In a couple minutes, we're going to see property number 4 that might simplify things for us in that regard. Before we see that one though, let's just look at a couple more. So here we're given log base 5 of 2 again, we're given log base 5 of 3 again, and we always know which one we have for free, log base 5 of 5, which is just 1, our third property. And we're asked, what is log base 5 of 3/2? If you remember our second property from above, we could rewrite this as log base 5 of 3 minus log base 5 of 2. Multiplication can become addition with individual logs. Division becomes subtraction. So using the values that they gave us, this will be approximately 0.6826 minus 0.4307. That sounds like a calculator problem. 6826 minus 4307. Oh, I forgot the point. 0.4307, 0.2519. Just about. If I wanted to check my answer, remember this is saying that I'll write it out. Log base 5 of 3/2 is approximately 0.2519. I can loop it and say, is 5 to the that, good English there, is it 3/2? Basically 1.4999, that's about 1.5 or 3/2. So this is just an example of that division subtraction transformation. What about this one? We know what log base 3 of 5 is. We know what log base 3 of 20 is. And we're asked to find log base 3 of 4. So my first instinct is, wait, but 4 is 2 times 2, and I don't know what log base 3 of 2 is. So how else can I rewrite 4 using a 5, a 20, and to be fair, there's also one other one that I know for free, log base 3 of 3. Make that a better 3. Log base 3 of 3 equals 1. How can I rewrite 4 using 3s, 5s, and 20s? Well, how about log base 3 of, gosh, my 3s are not doing well. 20 divided by 5. Which means I can split it up and subtract those. Log base 3 of 20 minus log base 3 of 5, which is approximately 2.7268 minus 1.4650, which would come out to be 7268 minus 1.4650. 1.2618. I can check it. 3 to the that, does it equal 4? 3 to the, oh gosh, 3 to my answer. Does it equal 4? Just about. 3.999738, just about 4. I feel confident there. So we've seen multiple examples breaking the 50 down, the 30 down into factors that we know, or maybe rewriting some of these division ones in 3/2, so 3 minus 2, or 4 we rewrote as 20 divided by 5 because we knew those values. All of these using our first 3 properties. But what about the most powerful property? Pun intended, the power property of logarithms. It's written over there on the right. And so the important part is definitely this right here. This is kind of stating what that rule is. It says log base b of x to the yth power equals y times log base b of x. Go ahead and get that down, and then I'm going to demonstrate with this problem on the left why this is such a powerful property. So on the left, we have 132 equals 14 to the xth power. How do I solve that? I mean, based on the last couple chapters, we would try to write 132 as 14 to the something, but 14 to the first is 14. 14 squared is 196, and so 14 to the what? It should be between 1 and 2, but how do I solve this? We're going to use logarithms, and we're going to use this property, this power property. Here's what I'm going to do. I am going to write log of 132 equals log of 14 to the xth power. Now, a couple pieces of background info. When I just write log with no base, by default, it is log base 10. It's something called the common log base 10, because we have 10 fingers, 10 toes, log base 10. What does this do for us? Well, let's take a look at that highlighted property. It says if we take the log of something with an exponent, we can actually move that exponent down in front of the log and multiply it. So what does that do for us in this problem? I took the log of both sides. That's legal as long as I do it to both sides. Log of 132 equals, I took the log of 14 to the x, something with an exponent. I'm just going to bring that down and say x times log 14. And this step right here, I'm going to put a star by, because this is a step you will use over and over and over again, taking the log of something with an exponent, moving that exponent down to the front. Because log of 132 equals x times log of 14. Log of 14 is just a number, and I can plug that in my calculator. And so I can divide by that number to get x alone. Log of 132 over log of 14 equals x. Use my calculator. There's that log button. It's right next to the 7 on my calculator. Log 132 divided by log 14, being careful with my parentheses. 1.8502, just about. That kind of makes sense because we said it should be between 1 and 2. 14 to the first was 14. 14 squared was 196. So 14 to the 1.8502. Sure enough, it just about equals 132 with a little bit of discrepancy because we rounded. Power property of logarithms. Let's see it some more. Given log base 4 of 6, so we're given that information, what log base 4 of 6 is. I also happen to know what log base 4 of 4 is, just in case that is required. That's the one we get for free. What is the value of log base 4 of 36? Well, take a look at the two ways we could do this problem. On the left, log base 4 of 36, I'll do it like we would have done it before knowing the power property. See if this makes sense to you. One 1.2925 plus 1.2925, 2.5850. Before we knew the power property, we could have solved this problem like this and said, well, 6 times 6. So break them up into individual logs and add them together. With the power property, how does that change things? Log base 4 of 36. Well, I could write that as log base 4 of 6 squared, right? 36 is 6 squared. And log of something with a power, 2 times log base 4 of 6, which is approximately 2 times 1.2925. And because you understand addition and multiplication, 2 times that number, if I remember to put the times in my calculator, 2 times that number will be exactly the same as adding it to itself, 2.5850. So the power property is just another way to solve these equations. We're just getting more tools in our tool belt with, if there's an exponent up there, if there's specifically if there's a variable in the exponent, there's an x up there. I don't know how to solve for something in the exponent, but I can bring it down by taking its log, bring it down to the front. Now I do know how to solve that equation. Try this one on your own. Try this one. I'll put my work on the screen and we'll see how it goes. 3.5424, that's what I'm getting. Using the power property, rewriting 49 as 7 squared, bringing that 2 down to the front, 3.5424. So all the problems till now have been somewhat, how do we handle problems, rewrite them with these log properties? And there have been multiple ways to do each one. This last set of 4 problems, we're going to be combining all these properties in different ways to solve for x. So take a look at the screen. 2 log base 7 of x equals log base 7 of 27 plus log base 7 of 3. And the question is just, can we find an x value that makes this true? We're going to use all our properties. We want to make it log base 7 of something equals log base 7 of something. That is our kind of our end game, because then we can do our trick that we saw earlier in the last section. 7 to the log base 7 of something equals 7 to the log base 7 of something. And then the 7s and logs cancel out and we can just solve. So our end game is to get just 1 log on each side. Log equals log, we can get rid of the logs. So on the left-hand side, how can we do that? Well, we're actually going to do that power property in reverse. We see this 2 out front here. Where did it probably come from? Probably came from up here. So let's put it back. Log base 7 of x squared equals, and what can I do with log base 7 of 27 plus log base 7 of 3? We're going to do our first property sort of in reverse. Log base 7 of 27 times 3, which happens to be 81. So log base 7 of x squared equals log base 7 of 81. Remember, now we can say 7 to the log base 7 of x squared equals 7 to the log base 7 of 81. You could also just say, well, log equals log. Their insides must match. We can get rid of the logs. X squared equals 81. X equals plus or minus 9. Maybe. I mean, everything's good up to this point, but remember those extraneous solutions that we talked about in a previous section. If we plug positive 9 in for x, do we run into any trouble? The answer is no. We can do log base 7 of 9. If we plug negative 9 in, do we run into trouble? Think about if we plug negative 9 in here, we're getting log of a negative number, which last section we talked about we can't have. So again, always be checking for those extraneous solutions. We can't use negative 9 because kind of like we've seen, if I tried to do a log base anything of a negative number, we get an error, non-real answer. So final answer, x just equals 9. What I would recommend is pausing this video and looking at each step for 5 seconds, 10 seconds, making sure you understand how each step came to pass, because there's a lot going on here. But let's look at this same type of problem a few more times. Okay. That is exactly the same problem. Don't know why it's duplicated, so we'll go ahead and skip that one. Let me just make sure. Yep, it looks exactly the same. Not sure why I had that in there twice. My bad. What about this one? Log base 6 of x plus log base 6 of x plus 5 equals 2. If you're feeling confident, if you feel like you're getting this, try pausing and working this out. It has a couple new wrinkles, but things that you actually do know you are equipped to handle. And if you're not feeling confident or you did pause it and try it, I'm going to start working through this now. I'm hoping that you see this left-hand side and you're saying, okay, so this is log base 6 of, we can multiply these together because they were added right here. So we can multiply them inside the same log. So we get log base 6 of x squared plus 5x equals 2. Now we don't have log equals log on this one, but we got to get rid of that log base 6 somehow. So what am I going to do? I'm going to say 6 to the left equals 6 to the right. 6 to the left gets rid of the log. X squared plus 5x equals 36. 6 squared. X squared plus 5x minus 36 equals 0, because I love factoring. That's always my go-to number one try for quadratics. X and x, plus and minus. Multiply to be negative 36, add to be 5, plus 9 minus 4. X could equal negative 9 or positive 4. So using all of our properties, combining things, 6 to the left equals 6 to the right to get rid of the log in order to find values that work. However, checking for extraneous solutions. If I plug negative 9 in, do I get a negative inside of a log? Absolutely. Negative 9 would ruin it just by going in here. It would also ruin this one. We would get errors in 2 spots. Negative 9 does not work. If I plug 4 in, does it work? Log, okay, so 4, this would just be positive 4. This would be positive 9. We can plug thing's gonna get positive, so that works out fine. X equals 4. All right, one more, kind of an abstract problem. Log base b of 8 plus 3 times log base b of n equals 3 times log base b of x minus 1. And our instructions are solve for n. Notice we don't even know what b is in this problem. We don't know what our base is. Is that going to stop us? No. So on the left-hand side, the first thing I see that maybe we could do is throw this 3 back up into an exponent. So log base b of n cubed. Same thing with this 3 probably, since it's just sitting out there in front of the log. And whenever you see a number like that in front of the log, a lot of the time, it's very common that you're going to need to put it back into an exponent using these properties both ways. So we got rid of those ones in front. Now maybe I combine the left-hand side, log base b of 8 times n cubed, since they're added together, equals log base b of x minus 1 cubed. And you might be thinking and wondering, well, we don't know what b is. How do we get rid of log base b? You're right, we don't know what b is. But I can absolutely do this. Even without knowing what b is, I know that b to the log base b will cancel out. I don't know what b is. Maybe it's 10, maybe it's 5, maybe it's 100. But b to the log base b cancels out. We get 8n cubed equals x minus 1 cubed. Got rid of the logs. They're new, they're uncomfortable. We just got rid of them. So if our instructions were to solve for n, I'm probably getting n by itself. I'll do x minus 1 cubed over 8. Cube root both sides. N equals cube root on top. Cube root of x minus 1 cubed is just x minus 1. Cube root on bottom, cube root of 8 is 2. 2 times 2 times 2. N equals x minus 1 over 2. So again, we're seeing some more and more advanced problems using these properties. Using these properties and saying, how can I combine? How can I separate? How can I consolidate in order to solve these problems? Can I factor? Can I use that power property? Can I use division? All of these properties are really important that you know when we're dealing with logarithms. I know logs are new, but I'm hoping that this practice, this video, gave you some familiarity, and you're going to solidify that with the practice problems that you are assigned. So take a look at those practice problems. You'll notice a lot of them look pretty similar to these. Circle any questions you have so you can ask about them. Always be sure to be checking for those extraneous solutions, like right here, the -9, which would cause us to have a negative in a log. Can't have that. Bring your questions to next time we meet. But until then, best of luck, and I will see you in the next video.